For question 8, so we have a table with different alloys. The atomic weight, density, atomic radius for 3 hypothetical alloys are listed in the following table. For each, determine whether its crystal structure is FCC, BCC or simple cubic. So it seems that for this question we are going to need trial and error methods. So not only the atomic weight, density and atomic radius are given. So what do we know for all these three structures? First of all, we know that theoretical density for any given material is going to be Na divided by Avogadro's number times volume of the unit cell, where this N is number of atoms in the unit cell, A is the atomic weight given here, Na is Avogadro's number, Vc is the volume of the unit cell. So let's start by considering each structure. For simple cubic, what do we have? We have only 8 corner atoms sitting at the corners. This is Z, this is X, this is Y. And the atoms are touching on the edges. Okay, so A is going to be equal to 2R. We have that. Also, if you calculate the number of atoms inside the simple cubic, 8 corner atoms, 1/8 of them are included. There's only 1 atom inside the simple cubic unit cell. For BCC, what do we know? Again, we have 8 corner atoms, but this time we have 1 body atom sitting at the center of the body, and the atoms are touching on the body diagonal. So a square root 3 is going to be 4R, and also we know that number of atoms inside the structure is going to be 2 atoms. And what do we know about FCC? If we do the same thing, so I've just drawn top, front and right side atoms. The number of atoms is 8 corner atoms plus 6 face atoms. That's going to be 4 atoms. What about the A and R relation? Well, the atoms are touching each other on the face diagonal this time. Then A square root 2 is going to be 4R. So for every structure, we have the A and R relation, and we have the number of atoms. The A and R relation is important to calculate the volume of the unit cell, since for all three structures, the volume of the unit cell is going to be A cubed. After observing these facts, we now move on to theoretical density calculations. Okay, so considering each cubic structure and theoretical density expression, start with A, the simple cubic case. Rho is going to be equal to 1 times 43.1 number of atoms times the atomic weight divided by Avogadro's number times the volume of the unit cell, which is A cubed. Now for simple cubic, A is going to be 2R, so 2 times the atomic radius, which is given in the problem here. Convert it to centimeters, take the cube. Then body-centered cubic case. So we are checking whether the density we get from either of these calculations will match the density given here. That's why this is going to be a trial and error method. So 2 atoms in BCC, 43.1, Okay, write the numerical values down. For BCC, what do we have? A square root 3 is 4r. Leave A alone to get this expression, qubit. And for FCC case, rho is equal to 4 atoms this time, and then this expression. Now for FCC is going to be A square root 2 is 4r, so 2 square root 2 times the atomic radius cubed. So if you calculate each numerical value for alloy A, the simple cubic gives a density of 4.9268. The BCC gives 6.4, FCC gives 1.7419. So if you inspect all of these, you will see, you will come to the conclusion that the structure must be BCC, since 6.4 matches that. The BCC density matches the actual density. Now we can do the same calculations for alloy B this time. For alloy B, the simple cubic case first. 1 times 184.4 divided by the Avogadro's constant times the 2 times the atomic radius, which is 0.164 times 10 to the power minus 7 centimeters cubed. When you calculate this, you will get 12.2991. Now, grams per centimeter cube. It's really close. Let's check the other two cases too. 2 times 184.4 divided by 6022 10 to the power 23 atomic radius. Now we are doing the BCC case, times 4 over square root 3 cubed. If you calculate this, you will get 15.977, so it's definitely not BCC. Let's check the FCCs too. Rho is equal to 4 atoms this time, 184.4 divided by 6.022 10 to the power 23 times 0.146 10 to the power minus 7 times 2 square root 2 cubed. If you calculate this expression, you will get 17 point, I think it's 393, I'm not sure. So it's definitely not FCC as well. So we come to the conclusion that B must be simple cubic. If you do the same thing for C, alloy C here, you will find that it fits into BCC structure.